Jai to all of you. My name is Dr. Ritish Kumar. I am going to give the lecture on the topic of measurement in microwave and radar engineering. So, measurement is a very important topic. So, in this lecture, I will cover the topic of VSWR measurement and impedance measurement and the dielectric constant measurement. What is the VSWR? So, VSWR is nothing but voltage standing wave ratio. So, I presume that you all are aware about the microwave test van setup that you all are that you all have seen in the laboratory as well. So, if I say the sequence of the microwave test van setup, it is looking like the first one is the klystron power supply, klystron tube, isolator, then a variable attenuator, frequency meter, then slotted section, and then detector. So, whatever the component you are studying in the lab, you have to attach that component after the slotted section, or we can say you have to attach this the device under test in between slotted section and the detector. So, let's begin the topic of VSWR, that is voltage standing wave ratio. Voltage standing wave ratio. So, as you can see, the VSWR has a high value and low value. So, first we will study how to measure the low VSWR with the help of slotted waveguide section. So, you can see this is a kind of microwave test vent setup. Here we can focus over the slotted line section. So, and a slotted line section with the help of detector we can detect the power as well. So, this is a nothing but a kind of slotted section waveguide you can see here. So, this is a waveguide and this is slot over the waveguide and this is a scale over the slotted section. So, you with the help of this knob you can move the reference lever from left, means backward side, and forward direction as well. So, how we can measure the VSWR with this kind of slotted waveguide section here. So, firstly we will study the low VSWR value. The threshold level of low VSWR is the less than 10. So, we can see for VSWR less than 10 we have to follow this kind of measurement setup. So, here you can see this is a pattern of VSWR that we have obtained through this slotted waveguide section here. So, as we can see here, here you can see in the pattern there is some maxima, minima, maxima, minima pattern you will get after receiving the power from this slotted waveguide section. So, how we can receive this kind of pattern? So, as we know, what is the VSWR? VSWR is the ratio of B maximum divided by B minimum, right? So, we have to identify maximum voltage and minimum voltage over the slotted waveguide section. So, here the we have to adjust the attenuator in such a way to get the minimum voltage over the waveguide. So, you have to move this knob either in a particular direction, that is in the forward direction. You will get a pattern like first the voltage maxima, then minima, maxima, minima. So, with the help of measuring devices such as VSWR meter and CRO or DSO we can say. So, with the help of DSO you can measure the maximum voltage, right. So, you can read the maximum voltage with the help of VSWR, with the help of DSO, and minimum voltage with the help of DSO. When you move forward move this knob in the forward direction. So at last you need to take the ratio of B maximum divided by B minimum. At last then you will get the VSWR for the low value. Now what will happen if you move towards the high VSWR, that is greater than 10, then you have to follow the double minima method. This method is known as double minima method. Double minima method, right? So here again with the help of slotted waveguide section, you need to find some points. Here you can see here, this is a pattern of VSWR. Here you can look it here that this is a B minimum value, and and this is the distance versus voltage distribution over the slotted waveguide section. This distance is nothing but the distance read over this scale, right? If you move in the forward direction or backward direction, right? So so you can see here this is a, just a minute, okay. So first you need to find the minima over this minima in the VSWR with the help of this slotted waveguide section. So in a particular location you will get some voltage minima over this scale. So you have to read this value. Suppose you will get at some d distance the proper minima you will get with the help of this knob. Now you can see you will get 2 points after moving a forward direction and backward direction with respect to this reference minima. Then you will get 2 points where the you will get where you get the under 2 times B minima. In other words, we can say this is the point where you will have the power of 2 times, right? So this is a doubling power points, you can say here, or under 2 times V minimum points here. So these 2 points is represented by D1 and D2. These 2 points you will get with the help of this knob. First you have to move in the forward direction, then you have to move in the backward direction, right? So suppose this is a D1 point and this one is D2 point, right? And in other in this you need to find what should be the value of operating frequency or operating wavelength. Then you need to find two minima point. So this is a suppose first minima point you have at d distance, and second minima point you have d double dash distance. So this the difference between two minima is equal to d double dash minus d dash is equal to lambda g by 2. So this value you already know about the slotted waveguide section, and with the help of this you can get the lambda z guided wavelength, right? So now the formula that you need to apply here is totally based on, you can see this is a cutoff wavelength that is represented by 2a for TE10 mode. TE10 mode is nothing but fundamental or dominant mode for the rectangular waveguide. So here we are using the rectangular waveguide in this example. So we need to consider the fundamental mode TE10 mode, and for this mode the cutoff wavelength is given by lambda c is equal to 2a, where the a is equal to dimension of the of the waveguide. So this value you can measure with the help of a scale, then you can put the value of A here, then you will get the lambda c, that is cutoff wavelength. Now how you can identify of find the value of lambda g with the help of this formula. You already know about the cutoff wavelength, and you know the operating wavelength. So you can get the operating wavelength with the help of operating frequency. So you can put the value of operating wavelength and cutoff wavelength, then you will get the lambda z. So I hope lambda z we can get directly from this equation as well, where the double minima method you can directly get the lambda z value by taking the difference between these two minima point. Then you will get, after applying, you know the lambda z, d2 you know, d1 you know, that is doubling power point. Then after putting the value of lambda g, d1, d2 in this empirical formula, then you will get the VSWR value, and uh, this method is applicable for the high VSWR value. So here you need to remember the formula, that is an empirical formula for voltage standing wave ratio, that is lambda z upon pi d2 minus d1. So this is the method of measuring the VSWR. Now the next topic, the impedance measurement. Here we are using the measurement, here we are using the magic tip to for measurement the impedance here. So how we can measure the unknown impedance with the help of non impedance. So this is a diagram, a cross sectional view of the diagram of magic T. This is a as we know, the magic T is a 4-port device, and here the port 1, port 2, port 3 and port 4. So by default we can say this is a E plane port, means E plane port, and port 3 is in the H plane port. So as we know, port E plane port act as a subtractor port when the apply input in the both the inputs at port number 1 and port number 2 are in the same phase, while the port number 3 or H plane port will act as a adder port. So we can say E plane port and H plane port will act as a complementary by nature. So how we can arrange the system? So you can see here, at port number 1 you have to attach the non impedance, that is standard variable non impedance. Here at port number 2 you have to attach the unknown impedance, that you need to find out the value. Now the at port number 3 you have to attach the microwave source, and port number 4 you need to attach a detector, where you have to find the value that is equal to 0 value, that is that's why we call this is null detector. Why we need to null detector here, next we will understand here. So first you have to apply the source, apply the power with the help of microwave source. So you know this magic T act as a power divider. So you know the scattering parameter of magic T as well. So here this alpha 3 is divided equally in these two ports. So we can say this is a half power point, or we can say this is 1 by root 2 points of voltage in terms of voltage. So that's why this is a 1 by root 2 alpha 3 and 1 by root 2 alpha 3, that is nothing but the half power points, or 1 by root 2 times of voltage points. So this is power divider you will get at port number 1 and port number 2. As we know, there is a mismatching occur at this port number 1 and port number 2 simultaneously. So suppose a standard impedance of a standard impedance of waveguide is the characteristic impedance of waveguide is 50 ohm. So this is different from this 50 ohm. We can say suppose characteristic impedance of waveguide is equal to Z0. So here the reflection coefficient is equal to ZL minus Z0 upon ZL plus Z0, where ZL is equal to Z1, right? So here you will get the reflection coefficient here. Similarly, you will get the another reflection coefficient here, that is equal to Z2 minus Z0 upon Z2 plus Z0. So some power is reflected from this unmatched impedances. So suppose this is a reflected power or reflected volt power. So under root 1 by root 2 alpha 3, you can reflection that because of reflection you have to multiply with reflection coefficient here. So this power is reflected back, or in terms of voltage we can write 1 by 1 by root 2 alpha 3 rho 2. So here because both the power, both the field should be in the same phase, that's why you have to take the negative sign here, because E plane port works as a subtractor port here. So this is comes into the picture. So what you need to do, so you have to adjust, or you have to arrange the variable impedance in such a way that, so you in such a way that you will then you will get the 0 at 0 at this detector point, 0 power detector point. So at what points it will become 0, when both impedance will become equal. That's why with the help of known impedance you can identify the unknown impedance, because at the same impedance value you will get the null detector at port number 4, or you can say at port number E plane, in the E plane ports. So with the help of this known impedance you can get the unknown impedance from with the help of this magic T impedance measurement setup. So I hope this one is clear to all of you. The next topic is the measurement of dielectric constant. So uh, dielectric constant is an important part or important parameter to define the medium. So to define the medium you have to know the parameter like sigma, mu and epsilon. Right? Sigma is the conductivity, mu is the permeability, and epsilon r is the dielectric constant, or we can say permittivity. So to define a medium, this is an important parameter. So so you can see here, this is a permittivity formula. Epsilon is equal to epsilon naught epsilon r, where a relative permittivity is defined. Relative permittivity is a complex quantity which is defined with epsilon prime minus j epsilon double prime, where you can write in this way, where tan delta is the loss tangent. So loss tangent is defined by the epsilon double prime by epsilon prime. You can say imaginary part divided by real part of the relative permittivity. The ratio of imaginary part and real part of relative permittivity is known as loss tangent. So so how can we measure the dielectric constant? So the method is known as cavity perturbation method. So with the help of again slotted section, we can measure the dielectric constant as well. So firstly you can see here the setup. This is a slotted waveguide section here, because waveguide has two ports, so port number 1 and port number 2 here, and you can see this is a you need to attach the VNA. What is the VNA? Vector network analyzer. Vector network analyzer, VNA. Vector network analyzer. With the help of vector network analyzer, you can get the scattering parameters, that is S11, S12, S21 and S22. So you can get all the scattering parameter with the help of vector network analyzer. So you can see here the setup. First you need to take the resonating frequency without considering the sample. So you can see here, this is a resonating frequency of this slotted section waveguide. So you can see this is a empty sample resonating frequency, and it is represented by with the help of f naught, right? So first you need to take the resonating frequency with the help without the sample, without considering the sample. Then after you need to measure the resonating frequency by filling the sample in between the slotted section here. Then this resonating frequency is slightly shifted to the some other location. Suppose this is f naught, then you will get the f1 here, and then you will get the f2 here, then f3 here. So by considering the sample in between the two ports, the resonating frequency shifted towards the reference resonating frequency, either lower side or higher side, right? So with the help of this given an empirical formula, here you can see this is a empty frequency and shifting frequency. So after putting this frequency in this formula, shifting frequency, you will get the epsilon prime, that is the real value of dielectric constant. Then by applying this formula you will get the epsilon double prime. So so this is a cavity perturbation method. By distributing the power receiving a port number 2, we can have the dielectric constant of the material. Why? Because as we know, dielectric constant and the relation between the quality factor and resonating frequencies. Quality factor bandwidth is equal to FR upon Q. How you can get the quality factor? As you can know the bandwidth of this resonating frequency as well. Suppose this is a bandwidth, you can consider the bandwidth point of this resonating frequency, and you know the resonating frequency as well. So you can get the quality factor with the help of this formula. So you can put the Q in this formula here. So with the help of this formula you can get the real value and imaginary value of the relative permittivity. So I hope this is a cavity perturbation method will clear to all of you. By shifting the frequency we can get the relative permittivity of the material. So I think these all the topics are clear to all of you. The first one, the how we can measure the VSWR, then the impedance measurement through the magic T, and lastly the topic is the cavity perturbation method to measure the dielectric constant. I hope these all topics are clear to all of you. Thank you.